Greetings to everyone. Today we are going to discuss about the second topic in the third unit is the stresses in the dams and retaining walls. Okay. So mostly dams and retaining walls. That is, dams is used to withstand the water or to store the water for irrigation and power generation process. Okay, throughout the year, so that it can have some pressure in the structure where we built. Okay, now because of that water, in order to retain the water pressure. Okay, similarly the retaining wall is used to construct, okay, now to withstand the earth pressure. uh, Maybe in the hilly region, okay, or else normal plain surface to resist the earth pressure. Okay, so in most dam cases, in the dams as well as retaining walls, the structure is used to withstand the stresses, okay, in throughout the year or throughout the lifespan of the structure. Okay, so this is the things. Okay, and the section is going to withstand the stresses and the stability of the dam. And for the stability of the dam, we need some minimum requirement in the bottom, that is width. Okay, now for the either dam or retaining wall structures. So because of that, it is going to withstand the entire pressure of the water or earth. Okay, now let us move on to the topic. So dams and retaining walls. A large quantity of water, a large quantity of water is required for irrigation and power generation throughout the year. So a dam is constructed. A dam is constructed to store the water for the above purpose. Okay, the stored water in a dam. The stored water in a dam exerts pressure force on the face of the dam where in contact with water. Okay, uh, so if it is dam, this is our dam structure. Okay, so if I'm going to store the water here, so here I can have some uh, pressure due to water, so it can be denoted by the letter F. So this is our dam structure, and dam is going to withstand by means of its stability. So for the stability, we need some width of the dam. Okay, either dam or retaining wall, the thing is same. Okay, then the retaining wall is constructed to retain the earth in hilly areas. In hilly areas. So it exerts, that is, it exerts pressure on the retaining wall where in contact with the earth. Okay, so in both the cases, it can have some base length, that is base width. Okay, so that if it is water or soil, okay, water or soil, it can have some force on the structure. Similarly, because of its own weight, it is going to withstand. Okay, so that the resultant force may occur. Okay, now because of this resultant force, it is going to withstand the entire thing. Okay, now let us move on to the types of dam. Types of dam. So here types of dam in the sense with respect to structure shape. Okay, uh, so there are commonly used things of the dam are two types. Okay, there are two types of dams used in common. Okay, one is rectangular dam, another one is trapezoidal dam. Trapezoidal dam. Okay, so rectangular beam in the sense the entire profile, that is it have uniform breadth throughout the section height. So here as well as here, it can have uniform width until throughout the height of the structure. Okay, if it is trapezoidal, then it can classify into further, that is water face vertical. Water face vertical. Second one is water face inclined. Water face inclined. So these two types we can have generally. So first case, which is nothing but water phase is vertical. So the structure will be like this. This is also one kind of trapezoidal. Okay now. And the second case, water phase also inclined. So like this. Okay. So here we can, it is going to withstand the water. So it can have B1 and B2. Similarly here also it can have B1 and B2. So two different profile are there in the trapezoidal dam. So here in general among these two, most preferable section is trapezoidal. Why we are telling the trapezoidal section is for easy of construction. Since the base width is high, so we can easily construct like as our wish. But if we are going to keep like a rectangular section, no, it will be little bit difficult for the construction. Now let us move on to the rectangular dams. So the figure is going to be like this. So B is the width of the dam. B is equal to width of dam. Let B is equal to width of dam. H is equal to height of the dam. So this is our ground level. So the total height of the dam is equal to H. So let H is equal to height of the dam. Height of dam. Next, we can have water in the structure, okay, on the upstream side. So this height is nothing but small h. Okay, so small h is equal to height of water. Next I said here because of water there will be the force F. Okay, so F is equal to force exerted by the water on the side of beam, sorry, on the side of dam. Okay, next we can have this is G is nothing but center of gravity of the dam section. Okay, next W, we can have the W. So W is equal to weight of dam. Okay, weight of dam per meter length of the dam. Okay, next the density W naught is equal to weight density of dam. Another one is another W, small w is equal to density of water or density of liquid stored. Okay, so this is the thing we can have with respect to this. Okay, now I said already, so the resultant force is going to act on the structure. Okay, now so this is our horizontal force due to water. Because of water force we can have this force. Because of dam weight we can have this W. Okay, so for these two the dam weight is going to act downward, water force is going to act horizontal. Okay, horizontal force. So the resultant we can have, so this is nothing but resultant force, resultant force R. Okay, so if I am going to take this is O. Okay, and where this position is B. Okay, and if I'm going to draw a tangent, it will meet at one point. This is nothing but D and C. Okay, so again, if the downward force is acting, no, that place I'm going to denote by the letter of N, and where the resultant will meet at one point, that point I'm going to take it as M. So this gap between the force, that is the place N and M, is nothing but X. Okay, so the X is equal to the distance of resultant force, the distance of resultant force from the mid section or midpoint of the dam. Okay, why we are telling this word, na, then after we are going to keep the while going for calculation of stresses. Okay, now this will be the eccentricity. Okay, the force is going to be act like a eccentricity, that x distance. So that's why we are telling this also. Okay, now let us move on to the calculation part. Okay, first of all we are going to have a force due to the force F due to water pressure, due to water in the contact side of the dam. Dam. So F is equal to density into area into height. So I forgot to tell one thing. So here the force is acting now. So this force will be acting at a distance of h bar, which is nothing but h by 3. Okay. So this is the value we are going to, sorry, h by, uh, okay, this is not a h bar. So which is acting at a distance of h by 3 from the base. Okay. Now let us move on to the force due to water pressure. So F is equal to gamma in, sorry, density into area into H. So for the area, we are going to consider per meter length. So per meter length, okay, or per meter width of the section. Okay. So now W into area, so height into per meter length into h bar. So this h bar we are going to take it as a h by 2. So F becomes W into h into h by 2. So it becomes W into h squared by 2, force F. This is the force we are going to have because of water pressure. Okay. Next, the weight of the dam. Okay, per meter length. The force F will be acting horizontally, acting horizontally at a height h by 3 from the base of the structure. So if we need, we have to remember this. Okay. At a distance of h by 3, the maximum force will be acting. So next, the weight of the dam. The weight of dam. So weight is equal to the density, weight density of dam. So the weight density of dam is nothing but on which material they have used for the construction, like concrete or masonry. Okay. Or either rubble masonry or whatever it may be. Okay. Now, so based on that, the density, weight density of the dam will change. Okay, multiplied with volume of dam. Okay. So volume of dam is equal to, volume of dam is equal to area of dam multiplied with length. So here the length of dam we have considered as 1 meter in the previous case also. Okay. So volume V is equal to area. So here area in the sense the total breadth into total height. Okay, that is our area. So B into H into length 1. So V is equal to B into H. Therefore, weight of the dam W is equal to weight density. Okay, W naught multiplied with B into H, the total height. So this is the another equation which is used to calculate the weight of the dam structure. Okay. Next, this weight of the dam, this weight of the dam will acting downward will acting downwards through the CG of the dam section. Okay, that is displayed in the figure. Next, so we can have two things, that is the force F is acting horizontally, W is acting downward, that is weight of the dam and water pressure. So the resultant force we can have R. Okay, so we have to calculate the value of R. Okay, for that, so this will be becomes O, and this place I'm going to take it as B, and this is D and C. Okay, now therefore resultant force R is equal to resultant force R is equal to root under F squared plus W squared. So this is the another equation to find out the resultant force. Okay, next, the angle of inclination, okay, with respect to the vertical axis theta. Okay, the angle made by the resultant with vertical face. So tan theta is equal to opposite side by adjacent. So opposite side here it is BD, adjacent side it is OB. So here with respect to force we are going to take. So BD is nothing but our horizontal force F. Okay, OB is nothing but our vertical force W. Okay, therefore tan theta is equal to F by W is the another equation for finding the angle of inclination. Okay, next we should move on to the distance. That is the resultant cuts the base. Okay, that is the horizontal distance between the line of action of W and the point through the resultant. Cuts the base. So from the figure, this is N. So the line of action of load, that is W, is acting and it is meets at the base is here, and the resultant is going to meet the base at here. So the distance between N and M we have to calculate. Okay, cuts the base. So the distance between N and M in the figure represents the distance between the line of action of W and the point through the resultant cuts the base. So x is equal to distance between M and N. Okay, so the distance x can be calculated using similar triangle rule, using similar triangle rule. Okay, from the figure, so in the figure we are going to consider these all. Okay, so W, F, R. So if it is going to meet at base, it becomes M and sorry N M. This is our base. So here it is O, B, D, and if the line is going to be here, it is C. So consider the triangle OBD and ONM. Okay, so NM is equal to PD. So here the height ON is equal to OB. So we already know that BD is equal to our horizontal force. Okay, and this distance NM we are going to call it as a X. Okay, and this height O2 N height is nothing but h by 3. Okay, so O2N, this entire height becomes h by 3. So Nm equal to X, On equal to h by 3, and BD is equal to, we know the force. Okay, now BD is equal to horizontal force F due to water pressure, and OB is nothing but our weight of dam due to its material. Okay, therefore X is equal to F by W into H by 3. So this is the another equation. We can calculate the X value in another form. Okay, now by taking the moment about. Okay, in other hand, by taking the moment about, by taking the moment of all forces about the point M. So if it is like this, then F into this distance. Okay, so F into h by 3, which is equal to, okay, W into X. So W into X. Therefore X is equal to F by W into h by 3. Okay, so we can use both the format in order to find out the value of X. So these are all the some formulas we are going to find out for calculating the pressure. Okay, that is if I need the force due to water, that is pressure due to water, F is equal to WH squared by 2, that is density of water into h squared by 2. H is equal to height of the water. Okay, and next one is the weight of the dam is equal to that the unit weight of the dam material multiplied with the breadth into height of the structure. Okay, Next, the resultant force R is equal to root under F square plus W square. Next, the resultant force direction is equal to tan theta is equal to F by W. Okay. Then the distance of resultant force to the that is line of action of weight of dam is equal to x. So x is equal to F by W into H by 3. So these are all the some formulas which we are going to use for the problem. Okay. Still we have to calculate the stresses. Okay, now that we will discuss once after discussing the problem related to this derivation. Okay, thank you.